Now let's look at set theory. Set theory is one of the most fundamental and important topics in mathematics, and it's also very important in computer science. It's also a large enough topic that there are entire books devoted to set theory. So what I'm going to introduce now will be just the basic concepts of sets and subsets and a few other things. Okay? So let's start with the definition. A set is a collection of objects. Now typically those things in the set will be related in some form, or they share some property. So like you might have a set of colors, right? And this, we'll see various ways to represent a set, but it might be something like red, green, blue. That would be a set. You might have, 1, 3, 5, ... So these are the positive odd numbers. So you can see there's a relationship here and a relationship here. But we can have things that don't necessarily seem related in the obvious sense. If you were walking into somebody's room, you might find, shoes. Say if they have a pencil in their room, a towel, a dresser. These are all related in the sense they're in the room, but on the surface they don't seem like the same types of things, but it's still a set. Okay? So if X is a member of or element of a set capital X, so this is lowercase x, capital X, then we write X is an element of X. Now you've probably used the word set in English before, and in many ways the definition is similar to what you've used, but it's not entirely the same. And let's talk about how it's different. So a mathematical set in a mathematical set, order doesn't matter. That is 1, 2, 3 is the same as 2, 3, 1. And there are no redundant elements. So we wouldn't have this 1, 2, 3, 2. Okay? So that's redundant. So this is really the set. And in fact, if we were to try to add something to this, we're combining sets here. And there's really a symbol for this, but I'm using plus since that makes sense to us right now. But if I were to, add these together with the set containing 2, it still is just 1, 2, and 3 because of the lack of redundancy. Okay? So how do we represent sets? We just saw one way. So let's say set representations. So one way would be list the elements, or as much as you can. So we might have something like this. A is equal to zebra, monkey, giraffe. Or these are animals present in Africa, for example, right? So this is a finite set because I can see there's 3 elements here. We also could have something like this. 0 plus or minus 1 plus or minus 2 plus or minus 3 ... Where you can see this is a set of all integers and this is infinite, hence the ... Okay, so that's one way to represent set, or there's 2 ways there, excuse me, but they're all about listing the elements. state the properties these set elements share. So it'll be something like this. C is equal to, and if X is an element of the set, then, and this is a vertical bar, X is an even integer less than or equal to 10. Right? So 6 would be in this set, 0 would be in this set, -4 would be in the set because they're all even integers. I didn't say they have to be positive. And negative numbers or negative integers can be even or odd. Let's say if X is an element of the set, then X is a math student. Lots of our examples we see in an introductory course discussing set theory will use numbers because there's lots of easy ways to do things, but it could be a set of people, which is what we're dealing with here. Another way would be to use a recursive definition. And what does that mean? We'll say we have something like this, like the Fibonacci sequence. Right. Used to seeing it like this. Typically 0 and 1 is the first two elements, and then as we move along, each additional element is the sum of the two previous ones. So 0 and 1 is 1, 1 and 1 is 2, 1 and 2 is 3, 2 and 3 is 5, 8, 13, and it goes on forever. So how do I define it recursively? So I can say f of naught is equal to 0, f of 1 is equal to 1, and then each additional element, f of n, is equal to f of n minus 1 plus f of n minus 2. That is the previous element and the element 2 times in front of it. So if I'm trying to get to 2 here, this would be this one plus this one is what we have here. So this is a recursive definition. All right, I'm making use of other values of f here to produce the current value of f. Now you're already familiar with some well-known sets. So you have things like this, the natural numbers. Now depending who you ask, that's either this, 0, 1, 2, 3, or 1, 2, 3, without the 0. I'm not going to get into a debate over which one I think is correct because I don't necessarily have an opinion on it. But some people say this, some people say this. Obviously, in certain contexts, whether or not 0 is there would matter. But that's a different issue, right? Set of integers. What's the difference here? Well, now we definitely have 0, but we have things like this. I will write ... minus 2, minus 1, 0, 1, 2, ... So it goes back to what I've had earlier. Okay, 0, plus or minus 1, plus or minus 2, plus or minus 3. This is an alternate way than what I just wrote now, but they're both a set of integers, right? This is supposed to be a funky cube. Set of rational numbers. Those are the ones that can be represented as a ratio of integers where the denominator is not 0. So that's P and Q, where both, we'll put over here, so we'll say Q is not equal to 0, and P and Q are elements of the integers. Okay, so things like 3/4, 5/16. It does not include things like pi, right? Because that's an irrational number. Set of real numbers. Okay. Set of complex numbers if you want to get into that. So these are well-known sets. All right. Let's talk now about the idea of a subset. So let's say we have these two sets. A is equal to 1, 2, 3. And once again, order doesn't matter. I just do it because it's easy to write it in order off the top of my head. And B is equal to 1, 2, 3, 4. Right? So we can say here that A is a subset of B if A contains no elements not in B. 1, 1, 2, 2, 3, 3. I just ran out of all elements in A. Every one of those is present in B, therefore A is a subset of B. Okay? But B is not a subset of A because it contains a 4. So how do we write that? Well, I could write this, where it's sort of a sideways U, and then there's a straight line underneath it. Or I can write this. Notice that A here contains fewer elements than B. Okay? So it's what we call a proper subset. Now in English, you may use the word subset, and when I hear the word subset being used in everyday English, not that I hear it every day, but in everyday English, I think less than what it came from, which is what we have here. But strictly speaking, you could say that C, we'll put it here, if C is equal to 1, 2, 3, 4, then it's also true that C is a subset of B, and B is a subset of C. They're not proper subsets, which is what A is, but they are considered subsets. So we don't have to have fewer elements than the other set to be a subset. And because both of these are true, this also means we can conclude that C is equal to B, right? Because 1, 1, 2, 2, 3, 3, 4, 4, same things. If this is sort of messing with your head, the way I remember it is I think of being like this. I could write that 4 is less than or equal to 5, right? But I also can write that 4 is less than 5. Both those are mathematically true. But it's also true, if you're looking down here and going, wow, how do I resolve this with this? It's also true that 5 is less than or equal to 5 because of the equality. I can't write 5 is less than 5, right? But I can have 5 is less than or equal to 5, and also 5 is equal to 5. So it's more like this. So that's the way I keep it straight. A is a subset of B. A is a subset of B. This also means A is a proper subset of B, which means it has fewer elements than B. Okay? And it's important to be able to construct subsets. Now there's a particular set that's also important, known as the empty set or null set. And we write it typically either as a set of curly brackets which have nothing in them, or this right here. This is not 0. It's not the Greek character phi. It's its own symbol. I don't know what the particular name of it is, but we have this symbol right here. But note that this is not the same as this or this, where this right here is a 0. Okay, let's talk about this one. This right here is a set containing the empty set. Sorry, empty set. This is technically possible, but it's not the same as this. This is the empty set. This is a set containing the empty set. So I actually could have written this as two sets of curly brackets like this. Okay? So this is possible. This is also possible, but it's not the same thing. I know that often in everyday English usage, people think of 0 as meaning nothing, but 0 is a number. So I'm simply saying this is a set containing a single number, just like This is a set containing a single number. It's not the same set, obviously, because 0 doesn't equal 99, but this contains a number, this contains a number. Neither of these is empty. One of the things that will kind of blow your mind is that the empty set is a subset of all sets. So if I have this right here, I can say then the empty set is a subset of this right here. You may be thinking, well, how can that possibly be? But remember, our definition was that this contains nothing not present here. So if I write it this way, which conceptually makes more sense to me, I'm looking and saying, well, is there anything here that I can't find here? No. Which is why this is considered a subset of all possible sets. Okay? So once again, it is possible to have an empty set within a set. So a set containing the empty set. Let's look at one last thing. And this is the power set of a set. So if A is a set, then there's probably different ways to write it, but this is one of the common ways. Make it look like a function of capital P. The power set, this right here, is the power set of A. All right? So what does that mean? Probably the most common example you'll see will be something like this. Let's say A is equal to ABC. So the power set is every possible subset that we can produce from A here. So P of A is equal to what? And let's write it over here to make it easy to sort of see what we have. But one, we could choose none of the elements. So we have the empty set. We could have just A. We could have B. We could have C. We have A and B. We have A and C. We have B and C. So 1, 2, 3, 4, 5, 6, 7. And then we could have a subset containing all the elements. Okay? And each of these is actually its own set. So this really should be this. So they're subsets of the original set, which are, of course, sets themselves. So if we're writing that here, it'd have we'll continue here. So 1, 2, 3, 4, 5, 6, 7, 8. There's all the elements of the power set. I was counting because we can know in advance. So if A contains n elements, separate this out, then the power set of A contains 2 to the n elements. In this case, there are 3 elements in A, so 2 cubed is 8, which is what we just saw here. So that's the power set. So that's our basic introduction to set theory, at least in terms of what a set is, what a subset is, what a power set is. There's a lot more to talk about in terms of sets, and I'll make more videos for those, but this will get us started. And then one of the videos I make will also show mathematical operations on sets. How do we combine sets? How do we find the overlap in sets? How do we find the elements not present in the sets? We can actually use logic with sets as well, and we'll see those in other videos.